Hello everyone. So recently I was interested in how PWMs work for the ATmega or any AVR almost because recently I had to work with it. I had to develop a medical alarm system for that, for which PWM was quite necessary for me to know. And as I was doing it, I found many similarities between how it might be generating that beautiful PWM from the register values that we assign to it. I really got curious on how it goes from software to hardware, and if hardware, where is it exactly stored? So in this video, I will mainly cover that only. I'd like to really say that most of the devices used here are literally from my semester textbook. That is, you have this 74138 3s28 decoder. You have this 194 74194 universal shift register. Then there's this 151. We have the 191 counter, hybrid counter. We have again those registers. We have a comparator using 7483, and yeah, that's the essence of PWM is really just registers, decoders, multiplexers, as well as counters. That's how you really get PWM. And of course, this complex circuitry which makes the beauty of PWM work. Without talking further, let's really delve into this. Uh, Firstly, let's understand what all things we have in a timer, a regular timer that we all might be familiar with. We will start with registers. So first and foremost, the ATmega that I'm targeting here is essentially an ATmega 64A, 64A, yeah, 16AU. Now again, because I had to work with this, and I'm specifically covering timer 0 here, which is an 8-bit timer, because timer 1 is pretty much more complex than just timer 0. Now let's talk about its registers. It has around 4-5 registers that is useful to us mainly. This is the timer counter control register 0. Now the next one is T count 0. This stores the timer count. Now the next one is output compare register 0. This one is used to um, do an action when the timer count reaches this value. The action could be resetting the timer, or it could be toggling a pin that is associated specifically with this timer 0. So if we open up the data sheet here, we can see that OC0 is attached to PB4 pin. This essentially means that PB4 is attached to timer 0 only, and no other pins are attached to timer 0. It has the timer interrupt overflow register. And it also has another one which is called as TMISK or something. This is the very essence of the video and also this circuitry I made here. One thing about this entire circuitry is that it is just one part of the entire microcontroller. To give you an idea, this is the block diagram of ATmega 64A, and you can see this data bus here. There are multiple other blocks obviously, but timer 0 is only one part of this entire complexity. Something about timers is that it's completely hardware based, it doesn't disturb the CPU. Let's quickly discuss how software is converted here. So this is the data bus. That this part is actually a decoder that's inside every single of those blocks. This data bus is where the values are parallelly passed on to various registers here. AVR CPU firstly fetches an instruction from the flash memory, decodes it, executes it, and then passes appropriate control signals and data to the data bus. Let's firstly discuss all the registers bits, and then we'll move on to the actual hardware. So TCCR is an 8-bit register. Now the first bit is force output compare. This bit is rarely used. The next bit is WGM 00. WGM stands for waveform generation mode. The next one is capture output mode, and this is the MSB bit. Then here's WGM, it's MSB bit. And finally we have clock select pins, about 3 of them. The next register is timer count. It is actually just a storage of the count, so I may not discuss this one. The OCR register is also a software writable register of 8 bits where we store a particular value. Now, what happens in this particular value is, let's say this is the full range, this is the start, this is the end of your timer counter. OCR is any value between this range at which an action can be generated. For example, it may be toggling down a pin, or it may be toggling up a pin, or it could simply be resetting the timer for precise tone generations. So the TIFI register it's actually a singleton register for all the timers. What I'll discuss is its last 2 pins. This pin is for indicating when this kind of a match occurs. The next bit is for timer overflow. This happens when timer 0 reaches its final value, and then it overflows and returns back to 0. That's when this bit is set high. This is the TCCR0 register. It accepts these values in this fashion. This is the MSB register, this is the LSB register, and it has these pins that are labeled. We'll be playing around with this exactly for generating a variety of PWMs at this point. This is the count register. This could be used for storing any value. We cannot use this to read. I did not implement that feature here. But yeah. The next register is output compare register, which does that function which I explained. Next comes the prescaler. The prescaler is this 10-bit flip-flop which converts our 16 megahertz signal to a variety of signals. Now ATmega, now what we simply do here is based on these bits. Now based on these bits, appropriate clock signal is selected using this multiplexer. That is then directly fed to this 8-bit counter. We have a comparator for implementing the OCR function. I'm taking mainly the A equals B output, since as soon as that condition matches, I want it to either reset or do some logic with it. Next, it feeds to this waveform generator mode selector marks. This selector marks is selected by the WGM bits here, purpose of which I'll explain later. WGM is quite literally just how quickly it resets the timer. So it takes 2 inputs currently. One input is from the timer completely overflowing, and one input of reset is from comparator. This one is basically used for setting our GPIO to any of the PWM modes. You can rather set it to normal, or you can set it to any of the PWM modes, which I'll be showing later. This block is reset, again a D flip-flop here. And it then goes to this reset circuitry. These are cleared, and then these are loaded by these lines here. And finally we have the interrupt block. The interrupt block is where two of my interrupts are coming, and I applied them using NOT gates because they were active low. I added a write function here. The read function could not be implemented due to convergence issues. Let's now quickly discuss about the bits inside this register here. So firstly, we have the waveform generation mode bits. Firstly, you have the 0-0 combination. This is MSB LSB. It works as a normal timer. That is, it resets after 256. It generates an interrupt in the interrupt register FR, and that is it. Next is phase correct PWM. It generates a PWM such that your square wave will be exactly symmetrical to your end lines. This is done by modifying this particular bit here, but of course due to complexity I did not implement it. Let's now make sense of this. This essentially means that we'll have a 16 MHz clock going to timer's input. This means we'll have just divided by 8 is 2 MHz, and this finally means 15.625 kilohertz going. This means that we'll have 62.5 nanosecond per count as 1, 0 to 1 or 2, 3, etc. Finally, this will be 64 microseconds. Suits us how much precision we want. We play around with these values and we find the exact whole number that matches our PWM requirements. Let's say our requirement is that let's set the prescaler to 100, which means 62.5 kilohertz will be feeding our timer. Converting that to time period is 16 microseconds. Let's generate this kind of a PWM where now I know that 256, this into 256 is 4096 microsecond or 4.96 millisecond as per theory. Let's say that we want a PWM that goes around like this and comes back like this. So now let's set this OCR value to 200. This is 256, this is 0. What will happen is that exactly after we should be getting 3.2 milliseconds. Last step is to set up register values as per our requirement. So TCCR0 will be equal to, now FOC can be considered as 0, it is not used. Now WGM, let's see what WGM should be. In waveform generation mode, we want our timer to not count the full thing, and we also want OCR to make changes to PB4, that is the pin. So we will choose this one, fast PWM, which are both ones. Now let's select the COM bits, non-inverting, that is 1, 0. And finally for the prescaler, this one, so it will be 1, 0, 0. And finally for the OCR register, since it is 8 bits, let's convert 200 into decimal. This is the value. with base 2. This is the one with base 10. So we shall put exactly this value in our OCR register. Firstly, what I'll do is I'll load the TCCR0 register. Now if I press A, that should now load my value to the TCCRO registers. And as you can see, values have been loaded. Now let's load OCR0 register with the value we have calculated. So I'll press C, and that loads the values here as well. And now we can simply go here and we will see our PWM come to life. Now if we quickly measure the time period, this goes low exactly at 32 point, which is exactly the value we calculated. And the time value calculated is exactly 4.092. This proves that the system is actually working. And now let's tweak some values to see various modes of it. We have currently seen the non-inverting one. Let's now visit the inverting one. The inverting one is nothing special really. It's just setting the bits for this mux through that register, since this and this are connected. We can also directly view through this, and so the output at that point is really just the inverted version of this, since the connections of the latches are inverted simply. Now in the fast PWM mode, we can also have the toggle function working. So toggle simply toggles the pin as soon as OCR match condition is seen. For toggle to work, we have to set COM to 0, 1. This means changing the bits here. So that's 0, 1, 0, 1, 1, 1, 0, 0. For effects to take place, you have to load it again. So and the register has loaded with the new values. So if we observe the new output, so as we can see, the total time period is still quite near the timer's time period. It's quite exactly the timer's time period. But yeah, it makes sense because OCR is encountered at the same point every time period. So next we have the normal timer, which is really just the timer going 256. After overflowing, this generates an interrupt by setting, I think so, this by setting this SR latch here, which already is set, and these will actually stay on until and unless we do a software write and put the 0 using this register right here. For which what we can simply do is we can put these two bits high, select the appropriate combination, which in this case is a 6, and those will be then overwritten. So what I'll do is I'll set these bits temporarily high, and these are also high, and what I'll do is simply write B and C, and you can see the timer overflow has cleared, but OCR is still there because probably it generated once more again. Now the last one is a CTC. CTC is used for generating precise tones from the OCR pin combined with the toggle output mode. Now this clears the timer after OCR match is met, and let's demonstrate it quickly. So firstly, we know that our OCR is positioned at 200, so it means that at this point it should have something. At this point it should toggle. The time period of this particular thing is 3.2 millisecond. So what we can do is we set that output mode to toggle, and we shall see a square wave with on-off time of 3.2 milliseconds. So deciding the register values again, it will be 0, 1. This will be toggle only, and this will be prescaled at 62.5 kHz only. Putting that here, now we again simply load it, we write it to the register using A, and that has reflected successfully. It means that we should be seeing the output here. And there we go, we see this toggle at exactly the 200th point. And the thing is that the timer also actually gets reset at this point. So it starts again, and exactly at 3.4, 6.4, sorry. Yes, it toggles again. So that's, yeah, with this, I could have also shown you setting the prescaler, but I mean, that's just setting CS bits, so not necessary. But yes, that's how PWM really works in essence. Thank you for watching.